The universe is filled with powerful events, from exploding stars to collisions of entire galaxies. Yet among all the known phenomena in the cosmos, none release more energy in such a short amount of time than gamma-ray bursts. These mysterious flashes of radiation are the most powerful explosions scientists have ever observed. For a few seconds, a single gamma-ray burst can release more energy than the sun will generate during its entire lifetime. To understand how extraordinary that is, imagine compressing billions of years of solar energy into a burst lasting only seconds. That is the kind of power involved in a gamma-ray burst. The story of their discovery begins during the Cold War. In the late 1960s, the United States launched a series of satellites designed to monitor nuclear weapons tests around the world. These satellites were equipped with sensitive detectors capable of identifying gamma radiation, the highest energy form of electromagnetic radiation. Unexpectedly, the satellites began detecting short flashes of gamma rays coming not from Earth, but from deep space. At first, scientists were confused. The signals appeared randomly across the sky and lasted anywhere from a fraction of a second to several minutes. It took years before researchers realized that these bursts were not related to nuclear weapons or nearby cosmic sources. They were coming from extremely distant regions of the universe. Once astronomers began studying them more carefully, they realized that gamma-ray bursts must originate from extraordinarily powerful events. The bursts were so bright that they could be detected across billions of light years. This meant that whatever produced them had to release enormous amounts of energy. Today, scientists believe there are two main types of gamma-ray bursts. The first type is known as a long gamma-ray burst. These events typically last more than 2 seconds and can continue for several minutes. Long gamma-ray bursts occur when extremely massive stars reach the end of their lives. When such a star runs out of nuclear fuel, its core collapses under the force of gravity. This collapse can form either a neutron star or a black hole. As the core collapses, the outer layers of the star fall inward and then rebound in a powerful explosion called a supernova. In some cases, this collapse produces narrow jets of plasma that shoot outward from the star's poles at nearly the speed of light. These jets carry enormous energy. If one of these jets happens to be pointed toward Earth, we detect it as a gamma-ray burst. The reason these bursts appear so bright is because the energy is focused into narrow beams rather than spreading equally in all directions. The second type is known as a short gamma-ray burst. These bursts usually last less than 2 seconds, but can be just as powerful. Short gamma-ray bursts are believed to occur when two neutron stars collide. Neutron stars are already among the most extreme objects in the universe. They are the collapsed cores of massive stars and contain enormous amounts of matter compressed into a sphere only about 20 kilometers across. When two neutron stars orbit each other, they gradually spiral inward as they lose energy through gravitational radiation. Eventually, they collide in an event that releases vast amounts of energy. The collision produces gravitational waves, as well as an intense burst of gamma radiation. These bursts can be detected across enormous distances in the universe. What makes gamma-ray bursts especially fascinating is how focused their energy is. The explosion itself does not expand equally in every direction like a typical supernova. Instead, most of the energy travels in narrow jets moving outward at nearly the speed of light. Because of this focusing effect, the total energy of the explosion can be far greater than what we actually observe from Earth. If we happen to lie within the path of the jet, the burst appears extremely bright. If we are outside the beam, we might not detect the event at all. Although gamma ray bursts occur far away from Earth, scientists have wondered what might happen if one occurred relatively close to our planet. Because the radiation from these bursts is so intense, a nearby gamma ray burst could potentially affect Earth's atmosphere. Some researchers believe that a sufficiently close burst might damage the ozone layer by breaking apart ozone molecules high in the atmosphere. The ozone layer plays an important role in protecting life on Earth by absorbing harmful ultraviolet radiation from the sun. If a large portion of the ozone layer were destroyed, increased ultraviolet radiation could reach the surface, affecting ecosystems and possibly contributing to mass extinctions. Some scientists have even speculated that past extinction events in Earth's history might have been influenced by nearby gamma ray bursts, although this idea remains uncertain. Fortunately, the probability of such an event occurring near Earth is extremely low. Most gamma ray bursts originate in distant galaxies billions of light years away. In addition, the jets produced by these explosions are extremely narrow. Unless Earth happened to lie directly in the path of the jet, the burst would have little effect on our planet. Despite the potential dangers, gamma ray bursts are extremely valuable to astronomers because they provide a window into some of the most extreme environments in the universe. When a burst occurs, telescopes around the world quickly turn toward the event to observe its afterglow. After the initial flash of gamma radiation fades, the explosion often produces longer-lasting emissions in X-rays, visible light, and radio waves. These afterglows allow astronomers to locate the host galaxy where the burst occurred. Because gamma ray bursts are so bright, they can be observed from extremely distant regions of the universe. Some bursts have been detected from galaxies more than 13 billion light-years away. This means the light from those events began traveling toward us when the universe was very young. By studying these distant bursts, astronomers can learn about the earliest generations of stars and galaxies. Gamma ray bursts also play an important role in modern astrophysics because they reveal the physics of extreme objects such as black holes and neutron stars. The jets produced during these events are powered by intense magnetic fields and rapidly rotating compact objects. Understanding how these jets form and remain stable is one of the major challenges in astrophysics. Recent discoveries have provided additional clues. In 2017, astronomers detected gravitational waves from the collision of two neutron stars. At the same time, telescopes observed a short gamma ray burst from the same region of space. This was the first direct evidence linking neutron star mergers to gamma ray bursts. The event marked the beginning of a new era known as multi-messenger astronomy, where scientists study cosmic events using multiple forms of signals, including light, gravitational waves, and particles. Ultimately, gamma ray bursts remind us how energetic and dynamic the universe truly is. Even though they occur billions of light years away, they reveal processes involving extreme gravity, nuclear reactions, and magnetic fields operating on cosmic scales. They are brief flashes lasting seconds or minutes, yet they can illuminate entire galaxies and travel across the universe for billions of years before reaching Earth. By studying these incredible explosions, scientists continue to learn more about the life cycles of stars, the behavior of black holes, and the evolution of galaxies across cosmic history. Gamma ray bursts represent the most powerful explosions known in the universe, and each new observation brings us closer to understanding the forces that shape the cosmos.